The tuning of a PSS involves adjusting the PSS's parameters to achieve the desired damping of the system. Proper tuning ensures that the PSS is effective in providing stabilizing signals and improves the power system's overall stability. The tuning of a power system stabilizer PSS is a process of adjusting the parameters of the PSS to ensure that it provides the desired level of damping to the power system. The damping provided by the PSS is critical to maintaining the stability of the power system, particularly during disturbances such as faults or sudden changes in load. The tuning process involves adjusting the PSS parameters based on the system's response to disturbances. The goal is to achieve the desired level of damping without causing excessive oscillations or instability in the power system. The tuning process typically involves a combination of simulation studies and field testing to ensure that the PSS is properly calibrated. The specific tuning parameters for a PSS will depend on the characteristics of the power system, including the generator and excitation system. In general, the tuning process involves adjusting the gain, time constants, and lead lag parameters of the PSS to achieve the desired level of damping. It is important to note that the tuning of a PSS is a complex process that requires specialized knowledge and expertise. Improperly tuned PSS can lead to instability and even blackouts in the power system. Therefore, it is critical to work with experienced professionals to ensure that the PSS is properly tuned and calibrated. How can we tune a power system stabilizer PSS? The function of a power system stabilizer PSS is to extend the small signal rotor angle stability limits of the power system by modulating the synchronous machine's excitation to damp the rotor speed oscillations. To provide positive damping, the stabilizer must produce a component of electrical torque in the rotor in phase with the speed deviations. Different studies shows example in which a rotor speed-based PSS is tuned using a single machine infinite bus system with the objective to achieve a minimum damping ratio of 15% for the system with PSS. Those studies cases corresponds to one step of the following tuning procedure. Step 1, base case without PSS. Case is used to analyze the stability of the system without PSS. A modal analysis is run to identify the dominant oscillation mode of the system, which has a frequency of 1.23 Hz and a damping ratio of 3.35%. An RMS simulation CalmSim is run to verify the time domain response of the system to a step change in the reference signal of the automatic voltage regulator AVR. Step 2, phase compensation requirements. The PSS phase compensation requirements are obtained from the Bode plot of the generator exciter power system GEP open loop transfer function calculated with the machine's inertia set to an infinite value. The Bode plot is obtained from the execution of the calculation of frequency response command ComFreqresp in which the input signal is the PSS input signal UPSs of the AVR, and the output signal is the synchronous machine's electrical torque SME. From the GEP transfer function, the PSS should ideally compensate 88.72 degrees at 1.23 Hz. Step 3, phase shaping. The PSS model is added to the synchronous machine's frame. The time constants of the PSS phase compensation blocks are chosen to match the ideal phase compensation requirement calculated in the previous step. The ComFreqresp command is run to obtain the Bode plots of the PSS transfer function GPSS and the compensated transfer function GEPX-GPSS. The numerator and denominator time constants of the lead lag blocks of GPSS are set to 0.256s and 0.044s, respectively, i.e. each block adding 45 degrees at 1.5 Hz. It is verified that the phase of GEPX-GPSS is 2.8 degrees at 1.23 Hz and lies within +30 degree in the typical range of electromechanical frequencies from 0.2 Hz to 2.0 Hz. Step 4, PSS gain selection. The modal analysis is iteratively run for increasing values of PSS gain K until the damping ratio of the dominant mode is at least 15%, the selected value being 24 pu. The time domain response of the system to a step change in the AVR reference signal is simulated and compared with the response without PSS step 1 in the same plots. The following scripts provided in the scripts folder of the project library can be used to aid in the tuning process. DPL command lead _lag _time constants calculates the time constants of two first-order lead lag blocks for given center frequencies and maximum angles. Python command wrap to 180 wraps the results of the phase Bode plot to plus or minus 180 degrees. It must be executed while the plot page with the Bode plot results is being displayed. A similar procedure can be applied to tune power damper controllers pod installed in inverter-based resources, fax devices, or HVDC converters. In those cases, the proper pod input and output signals must be selected and the COM crest configured accordingly. Here are the steps involved in tuning a PSS. Identify the oscillation mode. Identify the dominant oscillation mode in the system that needs stabilizing. One of the commonly used methods for identifying the oscillation mode is the modal analysis. Select PSS type. Select the appropriate type of PSS to be used based on the generator and system characteristics. The most common types of PSS are lead lag and washout PSS. Select tuning parameters. Determine the tuning parameters, which include gain, time constant, and washout coefficient. These parameters need to be optimized to provide the desired level of damping for the identified oscillation mode. There are various tools available for PSS tuning, such as MATLAB, PSCAD, or PTI software. Conduct a simulation. Run a simulation to verify the performance of the PSS. The simulation should include the PSS, generator, excitation system, and the power system. Various operating conditions should also be simulated to ensure that the PSS provides stable performance in different system conditions. Field testing. After simulation testing, the PSS should be tested in the field to confirm its effectiveness. Field testing should be done under various system operating conditions to ensure the PSS's stability and effectiveness. Fine-tuning. Fine-tune the PSS if necessary, based on the results of field testing, to ensure its effectiveness. Tuning of PSSs is a complex task and requires expertise and experience in power system analysis and control. Proper tuning of PSSs is critical to ensuring that power systems operate reliably and avoid instability and blackouts. There are smart techniques for tuning power system stabilizers PSS, including trial and error method. This involves adjusting the PSS parameters based on the response of the power system to different disturbances. The parameters are adjusted until the desired level of damping is achieved. Frequency response method. This involves analyzing the frequency response of the power system and adjusting the PSS parameters to provide the required damping at the critical frequencies. Model-based tuning. This involves using mathematical models of the power system to determine the optimal PSS parameters for the desired level of damping. Optimization-based tuning. This involves using optimization techniques to find the optimal PSS parameters that minimize a certain objective function, such as the time domain performance or the frequency response. The choice of tuning technique depends on the complexity of the power system, the available data, and the desired level of accuracy. It is important to note that the tuning of a PSS is a complex process that requires specialized knowledge and expertise. Therefore, it is critical to work with experienced professionals to ensure that the PSS is properly tuned and calibrated.